Hello, Calculus 2 students. We begin the semester by reviewing derivatives. This first page is just a picture of all the different derivatives that we might come across in this course. Several of these I assume that you've experienced in a Calculus 1 class, but maybe not all of them. For example, some teachers don't talk about these, so I'll talk about those briefly. The u's and the v's stand for arbitrary functions. For example, a u might stand for an expression like, 3x to the fifth plus 2. That might be what u stands for, some arbitrary function. Or u might simply be x, simple function. Or even u might be a constant. Whereas all of the k's, n's, and a's are specifically constants. Let's look through some of these. This first rule is saying that the derivative, and then remember that this little symbol here means do a derivative of the expression, so we're doing, that's called a prime sign. So I read this as k prime, and k stands for a constant, so it's like saying the derivative of a constant is 0. So if I say, hey, what's the derivative of 5? The answer is 0. What's the derivative of 20,000? The answer is 0. The next rule is constant times a function. So there's the constant, there's the unknown function. And when you do a constant times a function, the rule is the constant stays, so the constant does not go to 0 this time, and you do the derivative of the function instead that's next to it. A simple example of this would be like, what happens if you have 2 times x cubed? And I say, hey, what's the derivative of that? Well, the 2 would stay, and you would only do the derivative of the x cubed. So the 2 would still be there, and the derivative of x cubed, if you recall the power rule, or the 3 drops down, power drops to 2. So that's 2 times 3 times x squared. So in other words, 6x squared. The sum and difference rules, when you have a sum or a difference of two functions, or a sum or a difference, and you want to differentiate that, you just differentiate what I say term by term. So differentiate u, then v separately, and then add or subtract. The product rule. When you have a product and you're differentiating, a lot of students initially think that you can just do u prime, v prime. They just differentiate the u and the v separately and then multiply their answers. Turns out that that's not correct. It does not produce a correct derivative function. Instead, you have to use what's called the product rule, where you differentiate the first, which is u prime, times the second, which is v, plus the first, which is u, times the derivative of the second. The quotient rule. If you're dividing two functions and you want to do the derivative, you do the derivative of the top times the denominator, and then minus the numerator times the derivative of the denominator, and then all divided by the denominator squared. In the case of the product rule, it doesn't really matter which you consider the first. If I do this term first and then add and then do this term second, that doesn't matter. But in the quotient rule, it certainly matters because of subtraction. It matters that you get the correct derivative in the correct spot. The chain rule. The chain rule is when you combine two functions through composition. If you have u of v and you differentiate, then you should differentiate u and compose it with v. So you do u prime of v, but then multiply everything by v prime. Now, I really don't think it's all that necessary to have this particular expression right here memorized, because everything else in this table is using the chain rule, but in a specific context. From this point on, all of these are specific examples of this more general chain rule. And what really matters is that you know how to do all the stuff here in the box. All right, the power rule. If you have some sort of function raised to a constant power, then you bring that power down, times it by that function again, but a new power is 1 less than it used to be, and then the chain rule part is just multiply everything by the derivative of that function u. Let's just do a quick example of this. You can see it in action. If you have, say, 3x minus 1, and that's to the fifth, and then I say, hey, do the derivative of that. This 5 will drop down as a coefficient. The 3x minus 1 repeats. The new power drops to 4. But then the chain rule part is here. Multiply by the derivative of whatever is inside these parentheses, which in this case will be the derivative of 3x is 3, and then minus, and the derivative of 1 is 0, so that just goes away. So just times it by 3. And those are the pieces you need to remember, right, that you see here in this formula. The power drops, the base repeats, the new power is 1 less than it used to be, but then multiply all of it by the derivative of the base being this unknown expression u. A general exponential rule. This is a constant raised to a function. That's different than up here, which is a function raised to a constant, right? You don't use the same rules. Power rule is function to constant. General exponential rule is constant raised to function. exponential rule itself is when the base is e specifically. So let's say, as an example of this, let's say I had 2 raised to the 4x squared. And I say, hey, what's the derivative of this? Well, this is constant raised to function, so I'm going to use this rule right here. Well, there's 3 pieces you need to keep in mind when you do the derivative of this. It doesn't really matter what piece, they're all being multiplied, so it doesn't really matter which piece you do first. Let's do this part here first. You rewrite the original function, right, a to the u. So part of my answer is going to involve 2 raised to the 4x squared. Then I'll do that part next, times the natural log of the base, which is natural log of 2. And let's do the u prime last. And in front of this, you put the derivative of that exponent, which is using the power rule and the constant times function rule, you get just 8x. Now specifically, if the base of the exponential is e, this rule still gets used even in the case right here. It's just that the last part would be a natural log of e, but natural log of e is 1, so that part doesn't need to be written. Now in reality, we're going to be working a lot more with e to a function. We won't see this one as much. So a specific example of this, if you have, say, e to the 5x, and I say, hey, what's the derivative of e to the 5x? Well, one part of this is to just rewrite it, e to the 5x, and then in the front, I put the derivative of the 5x, which is 5. Right, so you get 5 e to the 5x is the derivative of e to the 5x. Natural, or logarithms, a natural log. If you have derivative of log base a is a constant, remember, of u, and u is a function, then you need to do, there's 3 things over here on this side. U is called the argument of the logarithm. You need to do its derivative, and then put it over the argument, and then times the natural log of the base of the log. So if I said, hey, we have a log base 2 of 5x. Let's do the derivative of this. Well, the argument is 5x. Put its derivative in the numerator. The derivative of 5x is 5. Then put the argument down in the denominator, and then also join it with a natural log of this base here, which is 2. And this would be the result. Now, in this particular case, the 5s would cancel, so you could just write 1 over x times natural log 2, but sometimes they simplify, sometimes they don't. But you need to remember these 3 pieces. Derivative of the argument divided by the argument times the natural log of the base. Now, we're not going to work with a lot of logs whose base is something other than e. Now, instead we're going to be working with natural logs, which are log base e. The formula right here applies here as well. You would do a natural log of the base. Well, the base of this ln that's already here is base e. So you would have, according to the formula above, you'd have a natural log of e sitting right here. But natural log of e is 1, so you don't need to write it. In other words, this formula right here is a direct result of using this formula, but in the specific case when a is e, the number e. So when you're differentiating a natural log of a function, it's just the derivative of the argument over the argument. So if you have natural log of, I'll put a 6x plus 1, and I say, hey, what's the derivative of that? Then you would put the derivative of 6x plus 1 in the top, which is 6 plus 0, so just 6, over, and then the argument. And there it is. Over here we have how to differentiate sine, cosine, tan, all the 6 trig functions. The fact that u could be any function, you have all these u primes present. That's just a chain rule happening. If your trig function begins with c, there's 3 of them that begin with c, notice that there's a negative, right, in the derivative. The derivative of sine is cosine. So when you see a derivative of sine, you know they're going to have a cosine involved. The derivative of cosine is going to involve a negative sine. Derivative of tangent is secant squared. Derivative of cosecant is negative cosecant cotangent. Derivative of secant is secant tangent, and derivative of cotangent is negative cosecant squared. If you remember that the derivative of tangent is secant squared, then its coversion, the derivative of cotangent, is going to be cosecant squared. If you remember the derivative of secant is secant tangent, then the derivative of the cosecant, the coversion, is the cosecant cotangent. Let's just do one example here. Let's do the derivative of cotangent of 6x squared. So the derivative of cotangent is negative cosecant squared. Now the argument of the cosecant squared is the same argument that's here, so 6x squared shows up again. And then the chain rule says multiply this trig function by the derivative of 6x squared, which is 12x. All right, so this is an example that is applying this general formula right here in the specific case where u is 6x squared. And the inverse trig functions, when you see arc sine, another way to write that, just be mindful, is put sine with a -1 power on it. This also means arc sine. Same thing, arc cosine. If you see, a cosine with a -1 power, that just means arc cosine. And the same thing for tangent. I don't know what's happening there. Tangent, arc tangent is also written that way. So these are different ways to write these. Let's do one specific case. Let's do a derivative of arc sine. So let's say we have an arc sine of 7x. And I say, hey, do the derivative of that. Okay, so the 7x takes on the role of the u. Right? The 7x is the argument. So we got to put the derivative of the argument up top. So we have to say, okay, 7x is the u, the derivative of that is 7, and then the denominator is the square root of 1 minus the argument squared. So we have the square root of 1 minus, and then the argument is 7x, put it in parentheses, and that's being squared. So in the end, if you got rid of those parentheses, this would look something like this. 1 minus 49x squared inside that square root. And by way of review, lastly, the hyperbolic sine and hyperbolic cosine. Your teacher maybe did not cover these functions in your Calc 1 class, so I'll just cover them briefly here. Sine with an h is called a hyperbolic sine, and then the u is the argument. And in the case of hyperbolic sine, it means it's actually a combination of exponential functions. It's e to the u minus e to the negative u all over 2. And the hyperbolic cosine, sometimes we just say sinh for hyperbolic sine and cosh or cosh for hyperbolic cosine. And the hyperbolic cosine is defined to be the average of the exponentials e to the u and e to the negative u. So add them together and divide by 2. But their derivatives look eerily like the derivatives of just sine and cosine. Like the derivative of hyperbolic sine, right here, is hyperbolic cosine. The derivative of hyperbolic cosine is hyperbolic sine. Notice a key difference, though, is that no negative is here. Unlike regular trig, right, the derivative of cosine is negative sine, but the derivative of hyperbolic cosine is just positive hyperbolic sine. Let's do the derivative of a hyperbolic cosine of 2x. All right, so when I say differentiate this, the argument is the 2x. So the chain rule says put the derivative of the argument in the front. So the derivative of 2x is just 2, so that goes in the front. And then the derivative of cosh is sinh. And then the argument stays the same. So you put a 2x back there for the argument of the sinh. And here's an application, right, of this rule in the specific case where u is 2x. All right, so that's all we want to say about this first slide, these review of derivatives that you learned in Calculus 1. Now let's do formally some specific examples. Okay, so find the derivative function of each function below. This first function is f of x. If you recall, there's different notations for derivative. I could say f prime of x would represent the derivative function. And this is a sum, so we're going to do the sum rule, which means I differentiate this and then differentiate that separately. So we differentiate the 6, we get 0, and then plus, and then we differentiate the x cubed, and we're going to use the power rule, which the 3 would drop down, the x would repeat, the new power would be 2, and then chain rule says multiply by the derivative of x, which is 1. We don't need to really write that in this case. So the derivative of x cubed is just 3x squared. Other ways that I can say that I'm doing a derivative, suppose this was presented as just y equals instead of f of x equals. You could just say y prime. This is one way to say a derivative, so it's just 3x squared would be y prime. Another notation would be, this is called Leibniz notation. That stands for the derivative of y with respect to x. So there's another way of saying that you've done a derivative. Next example, this illustrates the constant times function idea, right? So g prime of x will be equal to, the 6 is going to stay this time, right? Unlike in this case here where the 6, because it was isolated, it was 6 plus, the 6 went away. It became 0 when you differentiated. But in this case, it's 6 times x cubed. So this is constant times function. The 6 will stay. And you're just going to put next to it the derivative of x cubed, which is 3x squared. So when you simplify this, you just get 18x squared. Right, so in other words, the 3 just multiplied to the 6 that was already there to make an 18. And then the power dropped from 3 to 2. Here's a difference of two functions. So we're going to differentiate this term by term. We'll differentiate 4 over x separately from differentiating square root of x. This, if you recall, this is a good way. Before I do the derivative, I'm going to prep. I'm going to rewrite these. I'm going to say this is 4 times x to the minus 1 minus, and then this is x to the 1/2. Right. So I'm interpreting these as x to a power. And now I'm going to do the derivative. And I'm going to use the power rule twice. And the power rule says, okay, so I'm going to multiply the -1 to the 4 that's already there, so that gives me a -4. And then the power drops from -1 to -2. And then the chain rule says now multiply by the derivative of x, which is just 1, so I'm not going to write that. And then minus, and then do the power rule again. The 1/2 drops down as a coefficient, and the new power is 1 less than it used to be. 1/2 minus 1 is -1/2. And you can rewrite your derivative without using negative exponents and see what this looks like. So y prime is the same thing as, keep in mind this -2 power is only affecting the x. So the -4 stays up top, but the x goes down to the denominator with a +2 power, minus, also here, the -1/2 power is only affecting the x. The 2 is going to be down in the denominator, and joining it will be an x to the +1/2. And if you wanted to take this a little bit further, right, you could write this as -4 over x squared. That part we're not changing, but the second part, you could change that 1/2 power back into a radical. The first step here was not a derivative, keep in mind. Right, we just did a rewriting of the original, and then below the line I did a derivative, and then I rewrote the derivative. Okay, so here's a case of we have a function, just more derivatives that we're doing here. 2 times e to the x, this is constant times function, so the 2 is going to stay, and then I use the exponential rule on e to the x. Well, in the derivative of e to the x is itself times the derivative of the exponent. So the e to the x will be back there again, and then times, and then the chain rule says do the derivative of the exponent, which is a 1. So you really don't need to write that times 1. And we get the derivative winds up being identical to the original. This next case, though, is a little bit different. This is the e to the u situation. So we put the derivative, so the u is the exponent. We put the derivative of the exponent in the front, which is 2, and then rewrite the exponential, which is e to the 2x. This is the case where the derivative is twice the original. Right, there was a change. No change in the f derivative, but definitely a change in the g derivative. Here's a case where we have a constant raised to the x. I'm using r equals, so r prime would be our derivative. Or you could say more formally dr dx, the Leibniz notation, the derivative. And this is an a to the u situation right here, where a is 2 and u is x. So I'm going to put x prime here, which is 1. I'm going to rewrite 2 to the x. I'm going to do a natural log of 2. So you need those 3 pieces every time you differentiate, a general exponential. All right, so the first piece, and I'll do the derivative of that goes first, which is a 1. Then you just rewrite the exponential. Then the third piece is the natural log of the base. Now you don't need to write that 1. Once you sense that the derivative of this exponent is 1, you really don't need to write it. Just leave that off, and you have this derivative. And then we have a y equals natural log of x cubed, 8x cubed plus 1. This is a natural log of u situation, right? So I'm going to be using this formula right here. The derivative of natural log of an argument is derivative of the argument over the argument being the u. It's the word I use to describe that u position. So in this case here, y prime, or dy dx, the Leibniz notation. We put the derivative of 8x cubed plus 1 in the numerator. And the derivative of 8x cubed is 24x squared. And the derivative of the plus 1 goes to 0. And then we put that all over the argument, which is 8x cubed plus 1. A few more derivatives here to illustrate product rule, generalized power rule, and quotient rule. Here we're going to employ the product rule. It's good to recognize that this is a product here. We have a u times v situation being differentiated. So the result should be, oh, and notice the prime here. This is saying do the derivative of the thing that's in the parentheses. So we know that we're going to get, according to the product rule, u prime v plus uv prime. Everything I put in red is kind of what I'm thinking. It's just showing you the structure of the derivative I'm about to do. but if you want to skip writing all that red stuff and just go straight to the black, that's fine. So the derivative of x by itself is 1, so there's the u prime, times the second, which is natural log of 7x, plus the first, so plus u, which is just x, and then times the derivative of natural log 7x. So I get to use the natural log of u rule and put the derivative of 7x, which is 7 over 7x. And then we can simplify this a little bit here. So we get natural log of 7x plus, and then over here we just get a clean 1. Everything cancels, becomes just a 1. So there's our derivative. Another way to indicate that you want to do the derivative of something, so over here we just put this little prime up there. But if you put a dx in front of a function, this is called a differential operator. It means find the derivative of whatever's inside the parentheses next to it. This is a u over v situation. This is a quotient rule. So if I apply the quotient rule correctly, it's going to be u prime v minus uv prime all over v squared. Okay, so we have to differentiate the top, differentiate secant of 3x. Well, this is a secant of a function situation. How to differentiate secant of a thing, of an argument. We put the derivative of the argument in front, and then you do secant and tangent of that argument. Okay, so I'm going to follow that rule here. So to differentiate secant of 3x, put the derivative of 3x in the front. So the derivative of 3x is 3. And then we do secant of that argument. So secant of 3x times tangent of that argument. So tangent of 3x. And that's the u prime. So there's one, this is only the u prime. That's all I've done so far for the top. Times the v. The v is 3 plus x squared. And then minus. Then we do u, which is secant of 3x, times v prime. Well, v prime, fortunately, is not very complicated. If you differentiate the denominator, derivative of 3 goes to 0, and derivative of x squared is 2x. And then all over the denominator squared. So, right, 3 plus x squared, put it in its own set of parentheses, and then square that. I'm not going to bother simplifying this much more, but very often these quotient rules will simplify. But let's just move on to the next example. Here, this is going to be a case of the generalized power rule. Notice we have a constant times a function. So the constant -2 is just going to stay. And then the function is a base to a power, a function to a power. So the generalized power rule comes into play here. So this 5 will multiply down to that -2, so it makes a -10. The base repeats. This is important, so don't change the base. The new power drops to 4. So we got the first part of the power rule down. But then the chain rule component of the generalized power rule says now we need to multiply all of this by the derivative of what's inside the parentheses, by the derivative of the base. So the derivative of 3x is 3, and the derivative of tangent of x is secant squared. And finish up that derivative. And that would be an example using the generalized power rule. All right, that's slide 4. Okay, so the last slide for this review. And this is just to reiterate what the meaning of the derivative function is in the first place, like what do derivatives help us know about a function. So I've got a function here. It's a parabola, 1/2 x squared minus 4x plus 3. It's been graphed for you. I used Desmos to graph this. Let's go ahead and find the derivative function. I'm at the derivative of 1/2 x squared. This 2 will multiply to the half, making a 1. And then the power drops by 1. So the derivative of the first term is just x. It's 1x to the 1. The derivative of 4x is 4, and the derivative of 3 goes away. Now let's take an x-coordinate. I'm going to pick the x-coordinate right here, 2, and plug it into the original function and plug it into the derivative and see what the different results are telling us. So if I plug 2 into the f function, I'm plugging it into this rule right here. So square that gives you 4, cut in half is 2, and then plus 3 is 5, and then minus 8 is -3. So plug 2 into the function f, and you get -3 back. That's the output. That's the y-coordinate you're seeing right here. So you just found out this point right here has coordinates 2, f of 2. Now I'll plug 2 into the derivative function. F prime of 2. 2 minus 4 is -2. What this -2 is telling us is the slope of the tangent line. So if I were to draw a tangent line, the slope would be -2. The slope would be f prime of +2. Okay, so this wraps up our review of derivatives. The next video will be a review of integrals.